Hello everyone. In this video, we're going to be talking about Zorn's lemma, and in particular about the application of Zorn's lemma to abstract algebra. I'm going to be proving three results, one in group theory, one in ring theory, and one in linear algebra. And in all three cases, we're going to use Zorn's lemma to prove the result. Zorn's lemma was introduced by Max Zorn in about 1935, precisely because the results I'm going to prove were known using the axiom of choice, but the proofs using the axiom of choice were very cumbersome. So Zorn introduced this equivalent formulation of the axiom of choice so that we could use Zorn's lemma instead to prove these results in a more direct way. By the way, before I go on, I just want to say that I'm basing a lot of what I'm talking about here on notes by my colleague Keith Conrad on Zorn's lemma and some applications, which is a wonderful set of notes with many other applications that I'm not discussing here. So I highly recommend that you go and read this paper instead. Now, here you can find the statement of Zorn's lemma. Let S be a partially ordered set. Then, if every totally ordered subset of S has an upper bound in S, then S contains a maximal element. What we're going to do first is actually try to understand all these words, like what does it mean for a set to be partially ordered, what is a totally ordered subset, what's an upper bound, and what's a maximal element. And then we're going to apply Zorn's lemma to prove the results we want to prove in group theory, ring theory, and linear algebra. Let's begin then with some terminology. So let S be a non-empty set with a relation that I'm going to denote less or equal to. The relation can take many forms, so it's not always just less or equal to, but we're just going to use this symbol for simplicity. Now, remember that a relation R on a set S is actually a subset of the Cartesian product of S with S, so that the pairs that are in the relation, so if I have S and T are in the relation, then what that means is that S is related to T. Now, relation is a partial ordering if it is reflexive. So for every element of S, we have that S is related to itself, is anti-symmetric. So that means that if S is related to S prime and S prime is related to S, then we must have that S is equal to S prime. And if it is transitive, so that means that if S is related to S prime and S prime is related to S double prime, then S is related to S double prime. And a partial order is total if, so we say that the set is totally ordered if for any pair of elements S and S prime in S, we either have that S is less or equal to S prime or S prime is less or equal to S. Now, let's see some examples of orderings. For example, the real numbers under the usual less or equal to relation, it is a partially ordered set, but it is in fact a totally ordered set because any two real numbers, either A is less or equal to B or B is less or equal to A. The natural numbers under the same inequality is also a totally ordered set. Now, the natural numbers under divisibility, so we say that A is related to B if A divides B. So if there is a natural number n such that B is A times n, so A is a divisor of B or A divides B, then this is a partially ordered set because we have pairs of numbers. For example, 2 does not divide 3, and 3 does not divide 2. So neither 2 is related to 3 nor 3 is related to 2. So it is a partial ordering. Not everything is related, but we do have an ordering that is reflexive, antisymmetric, and transitive. Now, for example, if we have a group G, I can talk about the subgroups of G under inclusion, and that is a partially ordered set. Here I wrote an example of the group S3 and all the subgroups, and we can see that it is a partially ordered set. There is no total order because A3 and the subgroup generated by the permutation 1, 2 are not related. This is not contained in A3, and A3 is not contained in here. So it is a partial order. The trivial subgroup is contained in all of them, and all of them are contained in S3, but there are pairs of subgroups that are not related. Now, if I have a ring R, I can talk about the set of proper ideals in the ring, so ideals that are not the entire ring, under inclusion, and that is also a partial ordering. For example, if the rank is the integers, then the ideal generated by 15, the principal ideal generated by 15, is contained in the ideal generated by 3. Every multiple of 15 is also a multiple of 3, but not vice versa. So 3 is not contained in the ideal generated by 15. But the ideals generated by 3 and 5, that is not related, and this is not related. 3 doesn't divide 5, and 5 doesn't divide 3. So there is neither one of those containments is true. So it is truly a partial order. As another example, take V be a vector space over a field F, and consider the set S, which is going to be all the subsets of V of linearly independent elements. So these are subsets of vectors that every vector is just linearly independent from the other vectors in the same set. And we are going to consider those under inclusion. So for example, in R3, we could have the set just with this one element, this one vector, and then the set with these two vectors, then this is contained in here, and that is contained in all of R3. R3 itself is not a subset in here, so it's not everything in here is linearly independent, so it is not one of those elements, but these sets are part of that set S. This is another set of consisting of just one element that is also, well, one element, one non-zero vector is always linearly independent. So this is one of those subsets. But this one is not contained in this one, and this set is not contained in that one. So it is also a truly partially ordered set. No, it is not totally ordered. Now, within sets that are partially ordered, for example, the natural numbers under divisibility, we do have subsets that are totally ordered. For example, in here, if I take the powers of 2, that is totally ordered because a smaller power of 2 will be a divisor of a larger power of 2. So there is always a relation between any two powers of 2. Similarly, if I have a ring and I take the proper ideals, a ring that is a commutative ring, so these are just left and right ideals. So proper ideals in the ring, then this is, as we've seen, this is in general not totally ordered, it's a partial ordering, but we can have, for example, for any set of ideals, I1 through I, just a set I1, I2, I3 of ideals, I can construct I1 and then I1 plus I2, I1 plus I2 plus I3, and this will be totally ordered. This will be a chain of totally ordered ideals. So within partial orders, we do have subsets that are totally ordered, which is one of the things that are mentioned in the statement of Zorn's lemma. So also, let's define what's an upper bound. So if we have a partially ordered set and we have some other subset T, we say that an element B in S is an upper bound on T if for every element in T, T is less or equal to B. For example, if we have the real numbers under just inequality and take the subset T to be all the non-zero, all the non-negative real numbers, then there is no upper bound. However, if you take the set of negative real numbers, then 0 is an upper bound. And notice that the upper bound doesn't have to be an element of T, doesn't have to be a maximum element in T. It just needs to be sort of like what in real analysis sometimes we say sort of a supremum or something inside S, not necessarily in T. So for example, here 0 is not a negative number, but it is an upper bound within the real numbers for this set. Great. So now also, what does it mean for an element to be maximal? If we have a partial order set, an element M is said to be maximal if there is nothing above M, there is nothing that compares that M compares to. For example, so what that means is that if you have any element in S such that M is less or equal to S, then S is equal to M. So that is maximal. There cannot be something above M with respect to that ordering. For example, over the reals under inequality, then for the non-positive numbers, so the real numbers less or equal to zero, has zero itself is a maximal element. And that's maximal in here. The maximal element belongs to this set. R itself has no maximal element because if I take any real number R, then R plus 1 will be larger. So there is no maximal element in the entire set of real numbers. If I take proper subgroups of S3 under inclusion, then all the subgroups except the trivial subgroup are maximal, like we saw previously in that lattice of subgroups. So there is no subgroup in between A3 and S3, and there is no subgroup no that is strictly between the subgroup generated by 1, 2 and S3. So all of these are maximal under inclusion. Now we're ready to talk about Zorn's lemma. So this is a statement of Zorn's lemma. If S is a partially ordered set, and every time we have a totally ordered subset of S, it has an upper bound in S, not necessarily in the totally ordered subset, but an upper bound in S, then S contains a maximal element. So as I said, Zorn's lemma is actually equivalent, logically equivalent to the axiom of choice. Here I wrote the axiom of choice as follows. If you have a collection of non-empty sets, xi, then the Cartesian product of all of the xi is not empty. And it's called the axiom of choice because, well, to make sure there is something in here, you would have to pick an element for every xi, and that choice, being able to pick these infinitely many elements, possibly uncountably many elements, to just construct one single element of this direct product, of this Cartesian product, that is what the axiom of choice is about. But Zorn's is actually logically equivalent to the axiom of choice, and this one is easier to use to prove the following results in algebra. And for example, we're going to prove using Zorn's lemma, we're going to show that Zorn's lemma implies that every vector space over a field has a basis. And we're going to prove that the Zorn's lemma implies that every non-zero commutative ring has a maximal ideal. Now, you might think that, well, we are using this set theory result or set theory axiom, the axiom of choice, to prove such a statement. But it turns out that these are equivalent. That if you assume that every vector space over a field has a basis, every vector space and over any field has a basis, then that is actually equivalent to the axiom of choice and therefore to Zorn's lemma. And similarly, if you assume that every non-zero commutative ring has a maximal ideal, that is also equivalent to Zorn's lemma. So we are using Zorn's lemma to prove these results, but there is no other way around it because these are actually logically equivalent statements to Zorn's lemma itself. Okay, so let's prove a statement in group theory using Zorn's. So the theorem is the following. Let G be a non-trivial finitely generated group. Then every proper subgroup H in G is contained in a maximal subgroup M. So a maximal subgroup meaning that this is a subgroup of G that there is no any other subgroup in between M and G. Okay, let's see how the proof goes. So let G be finitely generated by G1 through Gn, and let G0 be the subgroup that we want to find a maximal subgroup of G that contains G0. So first, we're going to generate a sequence of groups G0 up to Gn, defined as follows. Define Gi by being generated by G0, and elements G1 through Gi up to Gi. So for example, G1 will be G0 and G1, G2 will be G0, G1 and G2, and so on. And then you see that by the time we reach Gn, then I have G0, but I also have G1 through Gn, so I have all of G. So Gn is definitely G, but it may be G at some earlier point. So let L be largest such that GL is not G, but the next one is already all of G. Now, we want to use Zorn's lemma, so I need to find a partially ordered set. My partially ordered set here is going to be S, and it's going to be subgroups of G, such that the subgroup GL that we just defined is contained in H, but GL plus 1 is not in H. In particular, something is missing from G in H, so these are proper subgroups. And I'm going to consider S under inclusion, and then you can check that this is a partially ordered set under inclusion. Moreover, GL itself, you can see that GL is a subgroup and GL is contained in GL, and GL doesn't contain GL plus 1. That subgroup is in S, so S is non-empty. Now, we need to check what happens with totally ordered subsets of S. So take T to be some totally ordered subset. So all these HIs in S are comparable. HI and HJ, there is always one of them is contained in the other. And we want to show that there is an upper bound. So what I'm going to create is a new set, H, which is going to be the union of all the HIs. I'm claiming that this is going to be an upper bound. In particular, I need to prove that this is a group of G, a subgroup of G. So let G and H be in H. Since it is in the union, some G in H will have to be in some HI, and H will have to be in some HJ. But since H and J, HI and HJ have to be comparable, so let's, without loss of generality, assume that HI is contained in HJ, then both G and H are in HJ. And HJ is a subgroup because it's part of S. It is a subgroup, so the product of GH and the inverses have to be in HJ, but HJ is also in H, so the product and inverses are contained in H. So H is closed under products and inverses, so H is a subgroup of G. Now, take that H, so this we have a subgroup. H itself cannot be all of G because GL plus 1 cannot be in H. If GL plus 1 was in H, then it has to be in one of the HIs. But the HIs in H in S are defined that this is not happening. So this cannot happen, therefore this cannot happen, therefore this cannot happen. Therefore, H cannot be all of G. Moreover, GL is contained in HI for every HI, and therefore GL is contained in H. That means that H itself is in the set S we defined, and moreover, every HI in our totally ordered subset T, every HI is contained in H. Therefore, H is an upper bound for T in S. And now we are in business, and we can apply, therefore, Zorn's lemma tells me that there is a maximal element in S. Call it M. Then M is in S, and in particular is a subgroup. M is in S, and in particular is a proper subgroup. And GL is in M, and since G0 was contained in GL, that means that G0, the subgroup we intended to be inside a maximal subgroup, G0 is contained in M. So it remains to show that M itself is a maximal subgroup. So suppose there is another subgroup in between M and G, but it is a proper subgroup. Could this be the maximal one? Well, if if K contains M, then GL is contained in M, and therefore GL is contained in K. And GL plus 1 cannot be in K because if GL and GL plus 1 are in K, then all of G would be in K, and K would be equal to G, but it is not. So this cannot be in K, and therefore K itself is also in our set S. But that means that M is a maximal subgroup. Since we know that M was maximal in S, then this containment tells me that M has to be equal to K, and therefore M is not just maximal in S, M is a maximal subgroup of G that contains G0, which is what we wanted to prove. Great. So now let's see an application of Zorn's lemma to ring theory. So we're going to prove that every non-zero commutative ring contains a maximal ideal. And in fact, we're going to prove something stronger. We're going to fix a proper ideal I, and then we're going to show that there is a maximal ideal M that contains I. So how do we show this? In a similar way like what we just did. Let R be a commutative ring and I be a proper ideal. And now consider S to be the set of all proper ideals, J's, that are in R, and they contain I. Now, this is actually a partially ordered set with respect to inclusion. I itself is a proper ideal and I is contained in I. So I is in S, so S is non-empty. And now let's see what happens with totally ordered subsets. So take T to be a totally ordered subset of S, so some ideals that are totally ordered. And I claim that this is an upper bound, that J, the union of all the Ji's, is an upper bound for T. So to prove that J itself is an upper bound, we need to first of all prove that it is an ideal. So take lambda and mu be constants in the ring R, and x and y be in J. Since J is a union of ideals, then x has to be in one of them and y has to be in another one. But because the those ideals are totally ordered, there has to be one of the containments. So let's assume that J alpha is contained in J beta, but that means that both X and Y are in J beta, but J beta is an ideal. So lambda X plus mu Y will be also in J beta, and therefore this linear combination is also in J. And therefore J itself is an ideal. Now notice that J is not all of R, so J is going to be a proper ideal, because if it was all of R, one would be in J. But if one is in J, it has to be in one of the elements of the union. So one would be in J alpha for some alpha, and that would imply that J alpha is not proper, but J alpha was proper. So one cannot be in J, and therefore J cannot be all of the ring. Now, J is in S because J is an ideal, it is proper, and I is contained in Ji, and Ji is contained in J, so I is contained in J. So J itself is in S, and notice that J is bigger than any of the Ji's in T, so J is an upper bound in S. So we have found an upper bound for any totally ordered subset of S, an upper bound in S. So now we're in business and we can use Zorn's lemma. Zorn's lemma now tells me that there is a maximal ideal, there is a maximal element of S with respect to inclusion that is an ideal because it is in S. I is contained in M because it is in S. And it will be actually a maximal ideal. Why? Well, let's suppose that I have this ideal and I have some other ideal in between, some other proper ideal. Could this be? Well, we know that I is contained in M, and therefore I would be containing K. We are assuming that K is not proper, and we know that M is maximal, so these two things would say that K is actually also in S, but M is maximal in S, and therefore we have that M would be equal to K. Then if M is equal to K in this scenario, then that shows that M is a maximal ideal of the ring R containing I, which is what we wanted to prove. Finally, let's talk about Zorn's lemma in linear algebra, and let's prove that every vector space over a field has a basis. And in particular, we're going to do something stronger. We're going to prove that if W is a linearly independent set, so a set of vectors in V that are linearly independent, then there is a basis B of the vector space that extends W. So this says that any linearly independent set can be extended to a basis. So let's see how this goes. Take V to be a vector space over a field F, and let's write a collection of linearly independent sets. As I said, that means that these vectors are linearly independent. This may be an infinite set of vectors. So what that means is that any finite set of them is linearly independent, and meaning that if I have a sum of vectors in the set that give me zero, but a finite combination of vectors that give me zero, so all but finitely many of these coefficients are zero. So if a finite linear combination gives me zero, then all the coefficients would have to be zero. That's what linearly independence means for these vectors. And now let's find a partially ordered set to use Zorn's lemma on. And what I'm going to do is use linearly independent sets that contain this initial independent set. Is that a partially ordered set? Yes, it is a partially ordered set under inclusion. It is non-empty because, well, this set of the UIs is already one of those W's. So this set is in S. And now let's see what happens with totally ordered sets. So suppose I have a totally ordered set of linearly independent sets, then we're going to find an upper bound. And I claim that the union of all those linearly independent sets is also a linearly independent set, and it will be an upper bound. First of all, these are all vectors in V, and these are actually all linearly independent. The vectors in W are linearly independent for the following reason. Suppose there are n vectors in W that are actually dependent, and there is a linear dependence like this. Then, well, these VIs are in W, but W is the union of these WIs. So each one of those VIs is in one of the W's, but the W's are totally ordered. So there is one of these W sets that contains all of the other ones, and uh, therefore all of the VIs are contained in one of them. But if these linearly dependence is happening in just one of the sets that which we know are linearly independent, then all those lambdas have to be zero, and therefore this linear dependence was just trivial, and therefore W is linearly independent. Therefore, W is a linearly independent subset of V, and we have that the set of these UIs was in each one of the WIs, and therefore it's in the union of all the WIs in W. So W also contains that. And therefore, W is in S, and therefore, because it actually also is above every one of the elements of the T of the totally ordered set, it is an upper bound for T. And we're in business and we can use Zorn's lemma. Zorn's lemma tells me that there is a maximal element in S, and M then will be a linearly independent set in V. Because it is in S, it contains the UIs. And it also tells me, because of the maximality, if I had another, some larger set that was linearly independent, then, well, this larger set contains the UIs and it is linearly independent, and K would be in S. But M is maximal in S, and therefore M is equal to K. And this fact actually will imply that M must be a basis of V. Let's see why. M is a basis. Consider the vector subspace of V generated by the linearly independent elements that are in M. And suppose that I don't generate. So I have a linearly independent set. If I generated all of V, then it would be a basis. So suppose it doesn't generate. If it doesn't generate, there is some element in V, some V in V, that is not in the linear space generated by M. But if it is not in the space generated by M, then this set must be linearly independent and larger than M, contradicting the fact that this is also in S and M is maximal. So let's see that this is actually linearly independent. Suppose there was a linear dependence that involves V and some vectors in M. If there was such a linear dependence, if lambda is non-zero, I could solve for V and put it in terms of the WIs, and then V would be actually in the space generated by M, and that would contradict this statement. So this cannot be, and lambda must be zero, but then it would give me that this is a linear dependence in M, but these are vectors in M that are linearly independent, so therefore all the lambdas must be zero, which gives me that M is in fact a basis of V that contains all the UIs. So that is exactly what we wanted to prove, and that is the end of this video about applications of Zorn's lemma.